So I want to talk to you today about some work that we were doing in this past year that I'm quite excited about. It's about using some techniques of dynamical mean field theory, I guess, to analyze what I'm going to call an adaptive Langevin diffusion. This is joint work with some wonderful collaborators, Justin Ko, who has just started a position at Syracuse, Bruno Luero, who is at ANS Paris, Yue Lu is here at Harvard, and Yendi Shen, who is now at CL. Okay, so the setting at a very high level, let me just set up the basic kind of thing that I want to talk about, which is an example of what I'm going to call learning through adaptive sampling. So this idea of trying to do parameter learning or model learning by drawing samples from some distribution is very widespread across a lot of different applications in statistics and machine learning. Early examples of this include instantiations of expectation maximization kinds of models and the invariable models, where you want to alternate between some E step and an M step in an EM algorithm. And oftentimes we run into situations where the E step that you want to evaluate, the expectation is intractable, and you might want to do sampling from a distribution to approximate that step. This paradigm arises also in contrastive divergence kinds of methods for maximum marginal likelihood estimation. These are problems of a similar flavor where I want to do maximum likelihood learning of some parameter, and I have a gradient of the log likelihood that is intractable to evaluate. And so again, I might try to draw samples from the distribution that's represented by my current model in order to approximate a calculation of that gradient. And then more recently, this kind of paradigm has also arisen in applications of fine-tuning of denoising diffusion models. These are applications where I have some distribution and I want to optimize a property of that distribution, and I only understand the distribution as implicitly parameterized by some score function. And so in order to optimize this property, I draw samples using some score-based sampler, and then I try to evaluate the property or the gradient of that property on the samples. Right. So these are just some examples of this paradigm. And what I want to just highlight maybe is that all of these applications have the following thing in common, which is that they're all sort of iterative procedures that try to iterate between some process of learning and some process of sampling. So what I mean is that in order to try to take some incremental update of a model parameter, I would draw samples from usually a high dimensional distribution of some kind. And then after drawing those samples, I would take a step in the parameter and I would repeat this process back and forth. And so what I want to talk about today is just a very natural idea in one particular example of this. I think that in all of these kinds of applications, it becomes natural to start to think about processes where these two things are happening simultaneously. Right, so I'm doing Monte Carlo sampling from some distribution, and as I run the sampling procedure to draw from this distribution, the target that I'm sampling from is going to continuously adapt based on the samples that I draw in a method that learns as well. And there's a nice general discussion of this in this paper, for example, by Mariana Corba this year. What I'm going to do in this talk is to focus on a particular setting of this and to try to analyze very precisely what happens. Okay, so the model that I'm going to just focus on for the talk is a very simple instantiation of this kind of paradigm. I'll just focus for simplicity on a linear model. Most of what I'm going to say today can be extended pretty naturally to single index or general or more general multi-index models. But for concreteness, let me just write down a linear model. So I have a response vector y that depends on linear projections of some input data x, and the projection vector is theta star. And I observe this perhaps with some error. And the setting that I'm going to assume is something that in statistics we would call random effects or Bayesian kind of setting, where the coordinates of this parameter vector theta star, this projection, are drawn from some prior. So I will assume that they're coming i.i.d from a univariate prior that I'm calling g star. The noise, for simplicity, let's say it's Gaussian, and I know the variance. And the question that I'm interested in that's going to motivate this kind of adaptive sampling paradigm is that I don't know what is this prior distribution g star. So as the statistician, the only data that I observe are my features x and my response y. And what I want to try to do is, given only this regression data, try to infer or learn what is this prior distribution g star. Okay. And so in statistics, this is a very old paradigm that we call empirical Bayes. It's a paradigm that goes back to the 50s due to work of Robbins and Stein. This is a paradigm that in statistical context has been studied much more extensively in settings where I sort of have I have independent observations that correspond to the independent draws of my latent variable. So for example, sequence models. But what we want to do is to study this in a context where I have some regression designs. I should say that one high-level motivation for this particular problem and what originally drew us into this work is that we were interested in applications arising in statistical genetics. In statistical genetics, this kind of a random effects linear model is sort of pervasive across analyses that they do. And you should think about in the genetics context, why is some trait of interest across a number of individuals? What's captured by this design is maybe some amount of genetic information about the individuals. And this prior distribution that we're trying to learn in that context represents what people call the genetic architecture of that trait. So it's going to represent what fraction of genetic variants actually contribute to this trait, how much of the variation is caused by the top 10% of these, and so on. And so there's a lot of interest in understanding for different kinds of traits how the architecture is different from each other and to sort of get some insights about what this distribution is. So I'm not going to focus too much about this application, but there is a long line of applied work in the genetics literature that develops various methods to try to solve this learning. And what I want to talk about in this talk today is a particular procedure that we're going to advocate for solving this learning problem, and it's going to have this adaptive sampling kind of form that I was talking about first. Okay. Great. So the outline of the talk, what I want to do is the following. So I want to just first explain what is this method that we're going to propose to try to do this learning. And then I'll give you a summary. So our main results are about an asymptotic analysis of the dynamics of this method. Without getting too much into the technical details, I just want to give you a qualitative summary of what are the kinds of results that we were able to show. And then I'll get into a little bit more technical, this kind of DMFT theory that underlies the analysis. And as Morgan was saying, please, if you have questions, feel free to. Okay, great. So let me start with just the method itself. So what we're going to explore is a method of learning this prior through a maximum likelihood procedure. Just for simplicity of discussion, let me posit a parametric model for the prior. You can do things non-parametrically if you want. But so if I have a parametric model for the prior maybe depends on some unknown parameter that I'm calling here alpha and rk. And this number k you should think about as quite small, maybe 2, 3, 5 in comparison to the sample size that I mentioned. Okay. And in order to learn this prior parameter, what we would like to do perhaps is to just maximize the likelihood of my data over this prior. And the likelihood here would be the marginal likelihood marginalizing over my latent variables theta. And so it's the expression that you see here. It's the likelihood of y given theta integrated against this prior. Depends on this. Okay. And the log of this likelihood with a normalization, I'm going to call f hat throughout the talk. This has a number of names in the literature. I'll use the machine learning lingo and call this the evidence of the parameter. Okay, so what we want to do is to pick the parameter alpha that maximizes this. So the most natural thing to try to do is to do a gradient-based optimization of this parameter alpha. I want to write down the gradient of this and follow the gradient direction. And the basic issue that arises in all such latent variable models of this form is that even if I want to evaluate the value of this evidence or if I want to evaluate a gradient of this evidence, these evaluations are usually intractable to compute directly, right? So I will need to compute some high-dimensional posterior integral over my space, theta and Rd. For the gradient of the evidence, if you just do a quick calculus exercise by differentiating through the log, you can check that the gradient of the evidence takes the form of evaluating a posterior expectation with respect to this parameter theta, right? So what I'm writing here is the gradient of the log prior density summed over all coordinates of theta. And what I need to do is to take an average or a posterior average with respect to the distribution of theta. And this is what the form is, right? And so because in this kind of a model, the gradient of the evidence is intractable if I want to evaluate this directly, this motivates the use of approximate Bayesian procedures, in particular sampling procedures, to try to approximate this gradient. Right? Good. So I hope we're all on the same page. So what I'm going to describe is a particular sampling procedure that we're going to suggest for doing this approximation. And I will try to motivate this procedure from a variational perspective. So what I want to do to motivate the sampling procedure is to write down the evidence that we're interested in optimizing in its Gibbs variational form. So the Gibbs variational form is that the evidence for a fixed particular value of the prior parameter alpha I can understand as the maximization over a candidate class of posterior distributions on this space of this quantity here. That's a sum of an energy term and an entropy term. This is what we call the Gibbs free energy. And this equality is exact because this Gibbs free energy is exactly a Kullback-Leibler divergence from this candidate Q to the true posterior distribution plus a term that's exactly the evidence. So if I optimize this over all possible Q, I'm going to recover the value of the evidence, and the optimizer is going to be attained at the posterior distribution of okay. Okay, so the purpose of writing the optimization in this form is that in order to try to think about how I want to maximize the evidence over this prior parameter, what we're going to do is to lift this optimization and think about maximizing this Gibbs variational free energy, right? So what I can try to conceptually do at least is to compute the maximum likelihood estimate by maximizing over this latent, this prior parameter alpha together conceptually with a maximization over all possible posterior laws on RD. And if I can solve this bivariate maximization, the maximizer over alpha in particular would be exactly. So what we're going to do is to do the most naive thing, which is to try to write down a pair of gradient equations for maximizing this Gibbs free energy now jointly over this parameter alpha and the posterior distribution Q. The gradient in alpha is just the usual I take this function, I differentiate this in alpha. When you differentiate this in alpha, what you see is that you get the derivative of this term. And then the expectation here, so if I'm evaluating this free energy at a particular current distribution Q, you get a form that looks a lot like the actual form, the gradient of the true evidence, except that you want to compute an expectation evaluated against your current distribution Qt rather than the actual posterior distribution of the model. Right? Otherwise, it's exactly the same expression. And then to define a gradient in Q, I need to specify some geometry on the space of distributions. And to motivate the sampling procedure that I'll discuss, we're going to specify a Wasserstein-2 geometry. So if I compute this gradient in a Wasserstein-2 sense, then by the kind of identification of JKO, this gradient equation in Q you can interpret as a Fokker-Planck equation for the evolution of the density of a vector theta in RD that's equilibrating towards a stationary measure. And the stationary measure, usually if I have a fixed prior or a fixed prior parameter alpha is the posterior distribution for that prior. And what's happening in this gradient equation is that this target that it's equilibrating towards is itself a time-dependent target, right? Because alpha is going to evolve simultaneously, and at each instance of time, this Langevin diffusion is going to try to equilibrate towards the posterior for that. Okay, so conceptually, this is the underlying motivation or idea behind the sampler. So what we're going to do in order to implement this or try to carry this out is to simulate this gradient flow equation in the Wasserstein space by just running a Langevin sample. And so now I have this parameter theta that's evolving in RD according to a Langevin diffusion. And what I need to do in order to, so if I go back one slide, what I need to do to run this gradient equation alpha is I need to be able to evaluate an expectation under my current distribution Q of this kind of average. And what we're going to do is to just evaluate this empirically by evaluating this average on my draw Qt for a single sample from this Langevin. Okay. And once I plug in this empirical evaluation, this leads us to a sampling procedure, which is what I'm going to refer to as an adaptive Langevin diffusion. It's exactly a procedure of the form I was talking about on the first slide, where we're running two things simultaneously at once. The first is that I'm running a Langevin sampling chain in high-dimensional space in RD that's trying to equilibrate towards a posterior distribution that's parameterized by this, what I'm calling alpha hat t. And at the same time, there is a temporal evolution of alpha hat t, my learned prior parameter, that's going to be driven by the empirical distribution of coordinates of my Langevin chain. Okay. And I should say that this kind of procedure, so it's a parametric analog of a slightly more involved procedure that we propose in initial work. This is with Le Yingguan, Yan Li, and Yihong Wu. What we're analyzing here is just a simpler parametric analog of that procedure. And this general idea has also been proposed independently in the literature. You can find this type of idea and work by Kunslim and Johansson, as well as Akuditz et al. Good. And so to make this a little bit more concrete, let me just show you a video of what's going on. Maybe this will help you develop some intuition for this. So I'm just showing here two very simple examples of parametric priors and learning this form. They're both Gaussian mixture examples. In the example up top, my prior model, I'm assuming that each coordinate of this theta is drawn from a Gaussian mixture prior with two mixture components. They're equally weighted, 50-50. And then what we don't know are the two mixture means in this example. To make the means individually identifiable, I'm making the variances a little bit different in these two components. Okay. And so what I want to do is to learn the structure of this prior from my initial regression data. And so what the video is showing is a video of this algorithm running, right? So what you're seeing on the left is a histogram of the coordinates of this Langevin chain in RD. So it has D coordinates, and here D is quite large. It's something like 1,000. And so we're initializing this Langevin chain just from i.i.d. random standard normal coordinates. And what you're seeing is that as the method evolves, the histogram of this distribution is starting to deform towards this Gaussian mixture. And then on the right is just a depiction of the prior parameter space. I have these two mixture means, alpha 1, alpha 2. I'm initializing the algorithm at both means equal to 0, so 0, 0. And what you're seeing is that as the algorithm evolves, the alpha parameter is moving towards what's being depicted as a red star, which is the true parameter in the simulation. You can ignore the heat map for now. I'm going to come back to what this heat map actually is. Yeah.
Are there multiple chains or just one chain where you're blending?
Just one chain. There's just one chain. Yeah, that's a great question. So I'll come back to this point. So in a lot of the previous literature on this, the proposal, I think the focus has been on settings where you're not in the high dimensional space to begin with, and you might run a lot of multiple parallel chains and average across the multiple chains.
Some self-averaging.
Here, exactly. We're going to rely on some self-averaging. The example on the bottom is something similar. It's a scaled mixture of normals example. I have 3 Gaussian mixture components here. All of the means are just set to 0. I'm fixing the variances also, and what I'm trying to learn are just the 3 mixture weights for the scale. So it's a reparametrization of this Gaussian mixture model. And again, on the left, what you're seeing is a histogram of the coordinates as they're evolving for the Langevin sample. And on the right, you're seeing, so we're initializing this algorithm from a guess where that's close to 0, 1, 0. So most of the weight is on the standard normal. And then as the algorithm runs, it starts to learn what are the true weights, which in this case are 3/5, 1/5. Okay, so are there questions about the method itself? So what I'm going to talk about in this talk is an attempt to understand or to analyze these dynamics. But I want to make sure the method itself is clear.
So should I kind of think intuitively, like I don't know how to think intuitively about whether if I kind of randomly initialize this method, if I start off in a place that's likely to be good or bad, in the sense that truly like you can construct by hand some bad examples.
Yeah, okay.
Like you sample and you kind of just confuse
Right.
yourself more and more or something.
Let me punt on this question. So this is exactly the kind of question that we wanted to try to understand in order to, so right, okay, so maybe this gets a little bit of motivation, right? So here are some questions that, so we wrote a paper about this method that proved some kind of, in a more abstract setting, weak kind of local convergence results, but we wanted to analyze a bit more precise exactly the kind of question you're asking. So here are a couple of questions that I think are interesting about this process. The first is that we're trying to simulate a dynamics for this prior parameter alpha hat t. The ideal dynamics is some idealized gradient equation, and what we're proposing is to use an empirical average for just a single realization of this Langevin chain. So there's just first a propagation of chaos kind of question of does this make sense, and do we get enough self-averaging for this to hold? And in particular, is this approximation valid on a time horizon that would be long enough to learn what the actual prior is? The second, just super high level question, maybe is starting to get at the kind of question you're asking, Boris, is this is a Monte Carlo method. So if I were to randomly reinitialize this method with different random initializations, how variable should we expect the learned prior to be across different runs? What is the source of that variability? And maybe a bit more concretely about what you're getting at is that if you think about this method morally as trying to optimize this marginal log likelihood, this evidence function, in a kind of model like this, there's no reason why this evidence should be convex or concave in alpha. And so it can potentially have multiple fixed points. We'd like to have an understanding, is the number of fixed points dimension-free, or can it potentially be exponentially large in the dimension in the sample size? What are the possible sets of fixed points to which these dynamics can converge? And if I were to initialize in various parts of the parameter space, which one would it converge to? And then I will show you some examples where, so I've shown you a couple of examples where the method seems to learn the parameter fine. I'll show you some examples where it seems to fail to converge to the true prior parameter for various reasons. In these kinds of settings where we don't learn correctly the right prior, I'd like to understand if this is a statistical issue, that I don't have enough data to identify what the prior parameter is, or whether it's an optimization issue that I'm trying to maximize some non-convex landscape and I'm getting stuck in some local optimum of this landscape, or whether it's a sampling issue that, if I were to be able to do this optimization correctly, I can do it, but I'm using a particular Langevin dynamic sampler and it's getting stuck. And so we ran a bunch of simulations of the method, and just by looking at the simulations, it's hard sometimes to distinguish what's actually going on and to differentiate between symbols. So one can try to give some answers to these questions in a general setting, where you just have a general design matrix, and I think such results are interesting, and we gave some results of this form in our first work. But what I want to talk about and focus on in this talk is we wanted to get at a much more precise answer to these questions, restricting to a setting of i.i.d. random design. So restricting to a mean field setting, if you will. And what I mean by i.i.d. random design is that the coordinates of this design matrix will assume are from some distribution. Okay, so let me get into just a summary of what are the kinds of results that we're able to show about this. So let me formalize what is the mean field setting. We're going to assume a proportional asymptotic setting where n, the number of samples, and d, the dimension of the problem, have a linear scaling. The ratio is converging to some delta. My design matrix, I'll assume, have independent entries with mean 0, and the variance is 1 over d, so that the variance of the signal per sample is comparable to the variance of the noise that we're assuming. The initialization, let me just, for simplicity, consider a non-random fixed initialization. You can, of course, consider a random initialization that's independent of everything else. And then the initialization of the Langevin chain, I'm just going to assume we initialize from some i.i.d. distribution. And then finally, our assumption about the model class for the parametric family of priors, we're going to assume that it's sufficiently smooth. And I'm not stating formally and technically what these are, but roughly we need to assume that it's log concave at infinity. And so what I mean by this is that there is a compact range under which this density might not be log concave, but out in the tails has some strongly log concave tails. Okay. So this is the setting in which we want to work. And I will try to explain two results. The first is this kind of propagation of chaos type of result, which says the following, that if I consider the high dimensional limit as n and d go to infinity, there is a deterministic process, alpha t, a continuous process evolving in this prior parameter space that's going to approximate my process of the learned prior on fixed time horizons. So for fixed capital T. And just as a teaser to this process is going to be described via dynamical mean field theory. This is a type of theory that arose in statistical physics due to Sobolinski and Sibelius. In the mathematics literature, to make this rigorous, this was first done for some examples of Langevin processes for the SK model by Benarus and Guillaume. And then recently, there's been a lot of interest in this kind of thing in machine learning. And I know there are a lot of local experts also in the audience about these kinds of techniques. The second result that I want to explain is, so beyond this propagation of chaos kind of result, I want to understand what happens for over a long time, right? So I want to understand whether my learned prior is actually going to converge to something sensible in this process. And so the additional assumptions I would need to assume for this are that there's some bounded domain in RK such that my deterministic limit of my alpha process is going to remain confined. In some models, this confinement is automatic because the objective function, the evidence, is actually going to go to infinity. But in other kinds of models, we might need to impose some kind of regularization to achieve this confinement. And then the second main assumption is that I'm going to assume that the set of posterior distributions for alpha belonging to this bounded domain satisfy a uniform log-Sobolev inequality with a dimension-independent log-Sobolev constant. And under these assumptions, what we're able to show is the following. So first of all, pointwise over all possible priors in this domain, if I were to look at the value of the evidence of this model with this normalization of 1 over d, that in the high dimensional limit as nd goes to infinity, this converges pointwise to a deterministic function, an evidence function that I'm calling f alpha without the hat. And furthermore, if I look at the limiting dynamics of my learned prior parameter as time goes to infinity, it's going to converge to some critical point of this function. Okay. I guess the important point about this result is that this function, whatever it is, it's some dimension-free limiting object. There's no dependence on n and d. This set of critical points is also some dimension-free set, and it's saying that the prior parameter will converge to a number of critical points that's independent of the size of the problem.
But that still depends on this delta, the ratio of data over.
Yes, yes. So the concrete description of this will depend on this n over d ratio, which is delta. I'll show you what is this description in a second, but for those of you who are familiar with this type of theory, this function f alpha is what we would call the replica-symmetric prediction for the free energy of this model. This prediction was first computed by Guo and Verdu and extended by Kawashima in the type of model that's kind of thing. If I were to put these two results together, let me just say what it implies about the learning dynamics. What it's saying is that for some critical point of this limiting evidence function, and for any error tolerance epsilon, there is some dimension-free time, t depending on epsilon, such that in the large system limit, my learned prior parameter at that time would be epsilon close to this critical point. This set of critical points would include the true parameter if my prior parameter class is well specified. It may or may not include other points, and I'll show some examples of this. Okay, so going back to the two examples that I was showing you videos of, this was the first example of just this two-component Gaussian mixture model where I'm trying to learn the two means of the mixtures. Let me explain what these heat maps are. So these heat maps are precisely a numerical evaluation of this asymptotic formula for the evidence on this problem, right? So one of the nice things about having this formula is that usually I can't even compute what the evidence is, but here the evidence will be characterized by some set of fixed point equations. I can easily solve fixed point equations and compute what it is. And what you're seeing is just a landscape of what the evidence function actually looks like in this model. I'm depicting by these two red points the local maxima of this landscape. So this red star is exactly the true parameter in this example, this -1,1. And it's sort of intuitive maybe in this model that there's going to be a local maximizer of the evidence if I swap the two means around and put one of them close to 1 and the other one close to -1. Right, so what you see is that there's another local maximum of the evidence function, which is not the global maximum at this red dot. As I'm varying across these panels, what I'm changing is exactly this ratio delta, which is n over d, the amount of oversampling. So we're starting here in a picture where I have a lot of oversampling, and here I have a picture where I have a lot of undersampling. You can see a few qualitative things about these pictures. One is that as I increase the amount of undersampling, the relative values of the evidence at these two local maxima become closer and closer to each other. What this means is that it becomes statistically much harder to distinguish which one of these is the true prior parameter. And then these curves that you're seeing are runs of the algorithm initialized from two different possible parameters alpha, right? So depending on you initialize that some parameter, and then there's some basin of attraction of each of these local minima, and depending on where you initialize, you might converge to one of these. Okay. So, oh yeah.
I was going to ask, do you have any sense of like something more quantitative, like the rate of convergence in T? Do you have any sense of how quickly that happens?
Yeah. In T is hard. Yeah. So it's a great question. It's related to the question that I think Yuting was asking earlier during Linnaeus talks. It's so to get something that extends longer in T, there are not very many results about this. So what you'll see is that this is based on some theory. One way to derive these kinds of results is based on some approximate message passing or AMP theory. The question is related to getting long time kinds of behavior for AMP, which has been done in some Gaussian model settings, but I think a short answer is that we're not there yet in the theory. You can also ask questions for a finite time horizon, just the rate of convergence to these asymptotic limits. That's a question that's a bit easier.
What do you believe it is, though? Like, do you have any sense of what it should be?
For a finite time horizon,
yeah.
It should be 1/10 for the convergence. And this is probably known in Gaussian settings, and one can be sort of implicit in some of the literature for not Gaussian. This last picture here is just, instead of plotting the learned prior, I can also track maybe something like the mean squared error of my Langevin sample. And this type of theory also gives predictions for corresponding to these local modes. What is the value of the mean squared error that would be achieved? It's being shown by these two dashed lines. The true prior, you would get a smaller error. This is the Bayes optimal error. And then the incorrect prior, you would get an error that's a bit larger. Great.
So can I just ask about these critical points? Suppose you just stay in this Gaussian mixture world.
Yeah.
And ask roughly how did the number of critical points scale with the number of mixture?
Yeah, it's a great question. For this kind of for this mean mixture question, so we don't have a very good understanding of this question. There are some conjecture. Yeah. So if I show you, for example, if I go to the second type of example I was showing where you're parameterizing by the weights, my conjecture here is that there's always a unique critical point actually of this evidence. But we weren't able to show such a conjecture. So we don't have a great understanding of that. Yeah. There is a regime in which one can get at an answer. So in the regime where your oversampling is very high and over D is large, the landscape of this starts to approach a landscape of just a Gaussian sequence model. In that setting, this is clearly that there's a single unique local optimum. Going back to the mean mixture, I think it's whatever we understand about the number of local modes of just standard Gaussian mixture models without a design, right? But moving beyond this highly oversampled setting, I think it's not well understood. So this is just the picture of the second kind of example where I have these three weights on a simplex. Again, what you're seeing is that as delta, the oversampling decreases, here it looks like, so when we numerically evaluated this limiting evidence in these pictures, it seems like there's only a unique critical point, which is exactly the true parameter. If you initialize the method at various different initializations, for a reasonably large amount of oversampling, it seems to successfully learn what the true prior is. At some point, this starts to break, and this point is certainly below the kind of uniform LSI kind of assumption that we're posing. When it breaks, so what I'm showing you here, this green curve is something where we initialize actually to the true parameter vector theta star for the Langevin, and under this kind of warm initialization, you see that it does learn correctly the true prior, but from random initialization, it seems to get stuck, and I believe this is an issue of Langevin mixing. Okay. Great. So for the rest of the talk, let me just spell out these results in a little bit more detail and explain what is the type of, yes.
Just going back to this picture, could you comment a bit on how this interacts with these like computationally hard phases and stuff like that?
I don't think this problem is actually computationally hard in the kind of Gaussian, in the mean field design setting that I'm talking about here. I don't think that there's actually like algorithmic hardness for this problem. The reason is that you can get a warm estimate of this. So you can estimate moments of the prior distribution by solving some moment equations. And you can sort of get a warm, if you want to initialize the method in some vicinity of the true prior, this is always possible. Good. Okay, so let me try to spell out the results in a little bit more. So I'm going to try to explain these two results that I stated. The first is this propagation of chaos, or this characterization of the asymptotic dynamics of this alpha. And this characterization is via this body of techniques known as dynamical mean field theory in this literature. With this small apology to the experts in the audience, let me try to explain a little bit what various parts of this equation are. So what this theory describes. There are two univariate processes that I'm here calling theta and eta. And these processes are representing the empirical distribution of coordinates of this high-dimensional Langevin chain, theta t. And eta is representing the empirical distribution of coordinates of x times theta. And so the structure of these equations is heuristically something like the following, that if I think about the evolution equation for a single coordinate of theta, we call it theta I, when you write down the evolution equation, there's some direct dependence on theta I itself, as well as the I coordinate of the true signal theta star. This is what's captured here. There's a term that's coming from the derivative of the log prior. And in our learn dynamics, this would be my learn parameter alpha hat. I'm claiming here that it's going to concentrate around some deterministic limiting value. And so in the limiting dynamics, it's just alpha. And then the rest of the evolution is that this theta is going to depend on the other coordinates of the system. And the structure of this dependence in this type of model is that if I look at the jth coordinate of x theta, so the jth coordinate of theta, there's a sort of 1 over root n scaled dependence of theta I on theta j. And what we're doing is summing this 1 over root n scale dependence across all coordinates. And because this dependence is via an entry xij of this random design matrix, these 1 over root n effects are mean 0 and they're i.i.d. And so by central limit theorem phenomenon, the aggregation of these effects is going to result in a Gaussian field in the limit. So what you see in this equation is that there's a Gaussian field variable, a Gaussian process U that represents this CLT kind of thing. The correlation statistics of U, the correlation kernel, the second moment statistics is what I'm calling here C eta, and it should be governed by the second moments of the coordinates of theta. Conversely, if I look at the ith coordinate, so the jth coordinate of eta, it's going to depend on some 1 over root n scaling xij of theta summed over all coordinates. So we're going to get a Gaussian field also in the dynamics of theta. This is one component of the theory. And then the second component of the theory is that so this coordinate theta I is going to, there's going to be some 1 over root n scaled effect on eta j. And this effect is represented as some small part of this Gaussian field. It's going to propagate over time, maybe for some time. And then when eta j interacts back to theta I, it's interacting back using the same randomness, right? So this entry xij that modulates this effect, at some time later, it's going to interact back. And so I'll get some xij squared, which is of size 1 over n, but it has a non-vanishing mean. And so what's going to happen is that there's a memory effect where if I now sum this across all coordinates j, there's some self-interaction of theta on the past. And this memory effect is reflected by this kind of this integrated response kernel. You have what I'm calling here this response kernel R eta ts integrated against past values of theta. And morally, what should be this response kernel? It should track how this perturbation, this little 1 over root n effect, has propagated over time in the eta process. So it should be given by a derivative of this eta process in the Gaussian field. Right? So you see this on the next slide. So we have these two processes. I can kind of define from these processes for the derivatives of these variables in these Gaussian fields, and the response kernel should be defined self-consistent. So the formal statement of the theory is in a fixed point nature as follows. So if I give you some correlation response kernels, I give you a deterministic limit for the alpha, I can define these processes. And then from everything that I was just saying, the correlation response kernels as well as this alpha should then be defined in some self-consistent way from the laws of the processes. The definitions are that the correlation kernel should be given by the second moment statistics of theta and eta in the form that I just described. More precisely, on the eta side is the second moment of x theta minus y, because I have a true signal. So that's what's represented here. And then the response kernel should be given by the expectations of these derivative processes that track sort of the propagation of this little this perturbative effect over time. And the structure of these equations in this kind of a linear model that we're studying is following closely this work of Celentano, Cheng, and Montanari in 2021. They were able to formalize the validity of these equations in a setting without this kind of an adaptive prior term and in a setting of a gradient flow. And so one of the first components of our analysis is that we try to extend this theory to a setting where you have this adaptively learned alpha and a diffusion term in the dynamics. Okay. And so the statement of the theorem is the following. If I view this whole thing as a fixed point system in these deterministic correlation response kernels, as well as this alpha, that in some domain of functions with at most exponential growth, this has a unique fixed point. And then over finite time horizons, almost surely as the system size goes to infinity, my learned prior parameter is going to converge this is in a uniform sense to this continuous process. My empirical distribution of coordinates of my Langevin sample, as well as the ground truth theta star, is going to converge in a Wasserstein 2 sense to the law of this theta t and this theta star. And the same thing happens on the x theta. So this is the nature of the sort of propagation of chaos. Okay, good. So the second thing that I wanted to say, so I guess morally, if I want to understand then what this process is doing over finite time horizons, the information is somehow, it should be contained in this asymptotic limiting equations, right? Somehow these equations carry all of the information I would like to know about the system, in particular, how this alpha parameter is changing over time, which is maybe my primary interest. Practically speaking, how to tease out this information from the system is, I guess, notoriously hard in this field because the kinds of equations that's describing this limiting system are somewhat complex. And so what I want to try to explain next is our efforts to sort of understand the long time asymptotics of this.
Can I ask you for
Yes.
do you get any like slightly simpler understanding of the system work in the regime where like n over d is very small? And presumably whenever n over d goes to 0, these equations are kind of trivial.
When n over d goes to 0, I'm not sure. When n over d is very large, the equations do simplify. Because when n over d gets large and larger, you start to approach the population dynamics. And when you start to approach the population dynamics, these equations will reduce to like the population gradient flow.
I see, but don't they become really simple when n over d goes to 0 as well? It's like you can't learn anything.
Yeah, if they go to 0, they might become trivial in a more trivial. They might simplify in a more trivial sense, which is that they don't do. Yeah, they might just not do it.
I guess for either of these regimes,
Yeah.
like, can you say something when either n over d is very large, like kind of asymptotically, like in a power series?
You can do perturbative expansions of this around d over n. And this will tell you, so the 0th order term of this perturbative expansion will be some population gradient flow dynamics. You can understand, the first order of this perturbative expansion to understand what is the leading order finite n effects to the population dynamics. You can certainly do these kinds of things. Yeah. Good. Great. Okay, so in order to try to understand, so what we want to do though is not just restrict ourselves to these kinds of regimes. I really want to get some understanding of what happens for general n over d. In this particular problem, I think this empirical based problem is just more interesting or perhaps more relevant in settings where you're undersampling, where n over d is less than 1. These are settings where you can't just sort of directly invert the design and kind of convert it to a Gaussian sequence model. And so there's a lot of interest in understanding this small n over d regime. Okay, so let me try to explain how we can get some understanding of the long-time behavior of the system. So this understanding begins with an interpretation of these correlation and response functions of the DMFT system. And the interpretations relate to sort of what classically are notions of correlation and response type objects for the high-dimensional Langevin dynamics. So the correlation function is simple. It's the 2-point correlation function of the process. If I give you 2 observable, let's say, of this theta vector and RD, I'm calling them A and B. This CAB is just the 2-point correlation between these observables at times T and S. And then in the classical theory of Markov processes, there's also a notion of a linear response function. So informally, what I'm denoting here as RAB is it's the infinitesimal response of observable A at time t if I were to perturb the potential of this Langevin system by some B at time s. And more formally, what I mean is the following. These are the original gradient equations that I'm running. You introduce a little perturbation b theta. For the purposes of this equation, think about ft as just a delta function at a single time s for now. So it's just 0 except at a single time. And it's a small perturbation, so it's epsilon times this. And then what this response is measuring is the derivative in epsilon, so the first order effect, of the value of the observable A at some time t with respect to f. So the influence of this. And so if f is a delta function, you're just going to pick up the response RTS. To actually formalize this mathematically, we consider some smooth envelope. It's modulated over time, and you integrate the response over time. So the existence of this kind of response function is sort of classically understood in non-adaptive systems. We can check that this response function exists and makes sense mathematically for a class of observables, including the coordinate observable functions, where I observe individual coordinates of theta, or the sort of residual coordinate observable functions, x theta minus y. And then the interpretation of the correlation and response things in DMFT, the correlation is easy to understand. So the correlation was supposed to represent the expectation of the product of theta s and theta t in the DMFT system, which is exactly the limiting inner product between the vectors theta t and theta s in Langevin. And then the claim of this theorem is that we can also interpret the response process in DMFT. And so in the limiting system, it was defined as the derivative with respect to this Gaussian field variable, which is a construct of this limit, but you can reinterpret this as the response in this of a perturbation of the original Langevin system, right? So what I'm saying here, what this is representing is I look at the dynamics of a single coordinate theta j, I perturb theta j, that same coordinate at some previous time, and I measure the size of the perturbation later, and then I average this across all d coordinates of the system, and the DMFT response represents this limit. And there's analogous statements for the residual observables and the other pair. The existence of the correlation response, it's technical. Maybe I don't want to just get into it, but so there's an explicit representation of what the response should be in the high dimensional dynamics. You can write down in terms of some Markov semigroup language and then do this analysis. The approach to show that this convergence of the response holds is a sort of leave one out or dynamical cavity approach. What we do is to perturb the potential for a single coordinate, track the evolution of that coordinate by itself, and then also track the evolution of the mean field of all the other coordinates. And using the fact that we know the DMFT approximation holds for the mean field of the other coordinates, you can kind of get this leave one out dynamics and understand that the response should be exactly. Okay. And the reason for understanding this correlation and response is because if I have these interpretations of what these things mean, then there is a sort of expected behavior of what these functions should behave like in settings where the Langevin chain is rapidly mixing. So in the kinds of log-Sobolev inequality settings I stated earlier. And the behavior is the following, that if I look at large enough times SNT, the process should be close to some stationary behavior. So this correlation function CTS should be time translation invariant. It should only depend on the difference T minus S. The correlation between some theta T and the ground truth theta star should just be converging to some constant. So for large T, it's approximately some constant that I'm calling here. And the response functions you can check should decay to zero in some quantitative sense. That if I look at a perturbation and a long time later, I sort of forgotten the perturbation because I've equilibrated to the equilibrium. And more quantitatively, we expect the following, that this time translation invariant component of the correlation function, it should be the integral against some spectral measure of modes of decay of the Langevin process, plus an additive constant that just represents the overlap of two independent samples from the equilibrium distribution. And then importantly, there's a relationship between the response and the correlation function where the response is related to a time derivative of the correlation function. This is known as a fluctuation dissipation relation. Okay, yes.
Which types of problems this would hold in? I mean, there's the
exactly.
effects in some system.
Right. So I'm about to state a result that says that in settings where you have a uniform log-Sobolev inequality, this has to hold. Beyond this setting, it's an abstract assumption. So there's a question of when you can check this. But I'll show you a concrete setting where we can check this. I should have clarified. This definition here, I'm thinking about a setting for now where I'm not learning the prior. It's just I have a fixed prior distribution, and it's just about standard Markov dynamics for a fixed prior. Okay. Some interpretations of these quantities, these C theta kind of objects represent the posterior overlaps. This represents the overlap between a draw from the posterior and the ground truth. C theta 0 represents the squared norm of a posterior draw, and this represents the overlap between two independent samples of the posterior. So this encodes the overlap. This measure mu theta quantifies the sort of decay of these overlaps at two finite times in the Langevin process when the process is at equilibrium. This iota here, importantly, is strictly positive. Okay, we're assuming that in this assumption that it is strictly positive, and this represents a spectral gap of the mixing of this process. And then finally, this relation here is known as a fluctuation dissipation relation. Okay, so going to Blake's question, one thing that we can say, for example, is that if this posterior law for fixed prior alpha satisfies a dimension-free LSI, then the set of conditions all holds. And the reason that this holds and the way you can check this is that we can check this directly for the high-dimensional Langevin process. We have a spectral gap due to this LSI, we have rapid mixing and things like this. And then by checking this for the high-dimensional process and pushing this to the limit, we can establish these properties for the limiting DMFT correlation response. And just to clarify, so in these high dimensional models, there's then the question of when does the dimension-free log-Sobolev inequality hold? I can tell you the following things. If my prior is globally strongly log-concave, then the whole posterior is log-concave, so the LSI holds. If my sampling ratio n over d is sufficiently large, then also my concavity or my convexity of the likelihood is going to dominate. So this is also a setting where the posterior is concave. And then the third slightly non-trivial setting where this holds is if for any delta, which is n over d, if the noise variable sigma squared is sufficiently large. So if I'm in a high enough temperature of this problem, then we also have a log-Sobolev inequality. This statement is an adaptation of this result of Bauer-Schmidt and Boddenau for the LSI and the SK type model. Good. Okay, so let me not dwell on this. So what this allows us to say then is the following. Okay, so we have this abstract condition about what we expect the DMFT variables to kind of behave like if the process were rapidly mixing. And my claim is that in this kind of a setting, we can read off from the DMFT equations what the stationary or long-time behavior of the process should be. And okay, so to state what this is, let me define two mean squared error quantities as the sort of the squared error between my base posterior mean and my ground truth signal in high dimensions, as well as the entry-wise posterior variance. You can read off theoretical predictions from what these are from the kinds of overlap quantities that I was describing a moment ago. And what I claim is that if this dynamical mean field system satisfies this time translation invariance set of conditions, then these mean squared errors that's implied by these correlation functions have to satisfy a certain system of scalar fixed point equations. And these are what are known as the replica-symmetric fixed point equations for this problem. Yeah. The forms of these equations are not super important here. It's just there are four scalar variables. Two of them represent these limiting mean squared errors. Two of them represent some amount of variance in a scalar Gaussian sequence model, like a scalar Gaussian channel. And there's some way to define fixed point equations for this Gaussian channel, I guess is maybe just a summary of this. We can say a bit more. So as time goes to infinity, what this theory actually shows is that the bivariate law of theta t and theta star, which represents the empirical, the limiting empirical distribution of coordinates of my Langevin sample and the ground truth, this whole law is going to converge to a law that's described by this Gaussian channel. Right? So if you care about things other than second moment statistics of your sample, you can characterize that as well.
Can I ask actually about this? Like, so
Yes.
suppose you didn't have like one of these systems where you knew you had like a nice matching the LSI.
Yeah.
Right. Then like, I understand you might not be exactly time translation invariant, but like, is there something that to suggest that you could be like a mixture of like time translation invariant things, like just kind of depending on which like sector you're sort of going to? You know, like it's not a crazy conjecture, but I don't know if that's within the realm.
Yeah, no, it's super interesting. I think that there are some models in which one can try to formalize this kind of picture where you sort of have more local regions of the posterior landscape where you have rapid mixing and you have large energy barriers between them and you have some local convergence. We haven't tried to push the theory in this direction. Something's going to say that. Interesting. Good. Okay, let me just spell out one corollary of this. So from everything that I've told you, if I just glue these results together, what we've essentially been able to show then is that if I have a posterior distribution that satisfies this log-Sobolev inequality, then the mean squared errors, the overlaps, as well as the empirical distribution coordinates of a draw from the true posterior and theta star, they're predicted by this asymptotic replica theory. Okay. In particular, in the settings where I know how to show a log-Sobolev inequality, I do know how to show it for all larger noise variances sigma squared. And in those settings, if I were to integrate this equation for the mean squared error, I can get a limit for the free energy. Yeah, so this is the evidence of the model, and so there's sort of an IMMSC type relation where I integrate the mean squared error, and I can get at the free energy. And so what this is saying is that the free energy in this model is also correctly predicted by this replica theory. And what this is accomplishing is a dynamical proof of the validity of this asymptotic free energy in a model like this. That's a bit different from the sort of usual proofs of how this go using Gaussian interpolation arguments, right? We've carried out something that derives this kind of limiting free energy purely from the dynamics of the process. Okay, just to, let me, yeah.
5 more minutes?
Okay,
57.
let me try to,
We can go a bit over time.
I'll try to wrap up in 3. Let me just explain. I think the perhaps one interesting idea of this is how to read off this static fixed point equation from the DMFT system, and let me try to explain how this goes. So the idea is this, and this is an idea that's it's in the statistical physics literature, I think, as I understand correctly. And what we did is to try to make this mathematically precise. The idea is that if I were to focus on on the long time behavior of this equation, so this was the DMFT equation, I put here the time translation invariant component of the response, and I consider the time translation invariant component of the correlation. There's a fluctuation dissipation relation between these two things. I can understand this response in this Gaussian field. I can sort of undo the marginalization. So the way these arose in the original DMFT equations is that I focus on a particular particle and I sort of marginalized over the effects of all the other particles. What I'm saying is that I'm going to reverse this marginalization. Think about this as sort of, again, marginalizing over some set of auxiliary variables. But the difference is that the auxiliary variables that I want to reinterpret this marginalization over have a much simpler structure. There's no random disorder, and there's no interaction between those variables. They're just independent OU processes given my dynamics data. And the claim is that it's mathematically equivalent to, if I have a response and a correlation kind of structure that satisfies a fluctuation dissipation theorem, this is mathematically equivalent to a marginalization over some infinite heat bath, an infinite collection of OU processes. If I want to formalize this approximation, I can truncate this heat bath at some point. You write a number of particles, capital M, and then I claim that these two processes are close. Now, the advantage of doing this is that this kind of process where I have some auxiliary OU processes, this is a Markovian process. I can now understand, just using standard analysis of Markov chains, the convergence of this. The equilibrium measure of this process is particularly simple because all of these are decoupled. They're just some Gaussian things conditional on theta, and I can easily deduce what is the this. And the technical part of this is to try to control the difference between these two things, and we do this using coupling techniques. Let me try to wrap up. So just going back to the original theorem, this is just a restatement of the theorem. Then if I now have this adaptive prior, then as long as this dimension-free log-Sobolev inequality holds over this restricted range of prior parameters, we can kind of push this through the theory and get the statements that I was saying earlier. Okay, let me conclude. So what I've told you is that in a Bayesian linear model with a parameterized but unknown prior, first of all, I can try to learn this unknown prior by using an adaptive Langevin diffusion where the chain is adapting simultaneously to the learned prior parameter. And then the main focus of the talk was that if I work in a setting of a mean field design, i.i.d. regression design, then I can characterize fully the trajectory of this prior parameter by some dynamical mean field type equations. And under some kind of condition for this DMFT system, roughly saying that the system needs to mix fast enough, we can analyze the long time limit of this learned prior parameter through the DMFT and understand that it converges to a fixed. These are the references. Thanks.